today's lecture we look at rank order clustering. Rank order clustering is another method to create part families and machine cells in the context of cellular manufacturing. We explain rank order clustering using an example. So, we consider this machine component incidence matrix. In this machine component incidence matrix, there are 7 machines represented by the 7 rows and 8 parts or components that are represented by the 8 columns. For the sake of illustration, we are looking at a small sized incidence matrix, whereas in practice the incidence matrix will be much larger than the size that we are looking at. So, we are considering a 7 by 8 matrix only for the purpose of illustrating the algorithm, understanding fully that real life matrices are much larger. Now, we follow the basic notation where a 1 represents that part number 2 visits machine number 1 and a blank or a 0 indicates that part number 3 does not visit machine number 1. So, there should be a 0 here indicating that it does not visit. Just for the ease of representation, we replace the zeros by blanks or blank spaces, and a blank space represents that the part does not visit the machine. Now, rank order clustering is a simple algorithm that has been used extensively based on very simple principles. What we do now is we try and create a certain weight for each position. For example, we first look at clustering the rows or rearranging the order of appearance of the rows based on a certain criterion. Now, the criterion is as follows: each row has 8 elements representing the 8 positions corresponding to the 8 columns. For example, row 1 can be seen as 0 1 0 0 0 1 0 1. Now, we try and give a weight to each of these 8 positions, and this takes a weight of 0, which is this takes a weight of 1, which is 2 power 0. This takes a weight of 2 power 1. This takes a weight of 2 power 2, which is 4. This takes a weight of 2 power 3, which is 8. This takes a weight of 2 power 4, which is 16. This takes a weight of 32, 64 and 128. So, these are the weights that are given to these positions. So, the weights corresponding to these positions are, this is seen, the positions are considered from the right, and the rightmost position has a weight of 2 power 0, which is 1, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6 and 2 power 7. So, the weight corresponding to the first row is, this has a weight of 1, this has a weight of 4, this has a weight of 64, because this is 2 power 7. So, the weight is 64 for this, the weight is 4 for this, and the weight is 1 for this, giving us a total weight of 64 plus 4 plus 1, which is 69. Now, this row, this has a weight of 4 and this has a weight of 16. This is 2 power 2, this is 2 power 4. If you go back, this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6 and 2 power 7. So, the actual weight is 0 into 2 power 7 plus 0 into 2 power 6 plus 0 into 2 power 5 plus 1 into 2 power 4 plus 0 into 2 cubed plus 1 into 2 square plus 0 into 2 power 1 which is 2 plus 0 into 2 power 0 which is 1. So, 16 plus 4 gives us a weight of 20. Now, here the weight is 128 plus 8 136 plus 2 138 plus 1 139. Here the weight is 64 plus 32 96, 96 plus 1 97. Here it is 128 plus 8 136 plus 2 138. Here it is 64 plus 32 96 plus 1 97 and here it is 16 plus 4 which is 20. So, the weights corresponding to each row are computed by giving weights to column positions. So, the weights are 69, 20, 139, 97, 138, 97 and 20. Now, the rows are rearranged according to the decreasing order or non-increasing order of the weights. So, 139 comes first, 138 comes second, there are 2 with 97, we can use either 4 first or 6 or the other way. Then there is 1 with 69 and then there are 2 with 20. So, the order will be 3 comes first followed by 5. So, 3, 5, 4, 6, 1, 2 and 7. So, the order will be 3, 5, 4, 6, 1, 2 and 7. That is the order in which the rows are arranged. So, now go back, the rows are arranged. Row 3 has 1 0 0 0, 1 0 1 1, now 1 0 0 0, 1 0 1 1. Just the rows are rearranged, the columns are kept intact. So, from this matrix, by giving weights of 1, 2, 4, 8, 16, 32, 64 and 128, we find out the weight corresponding to each row and rearrange the rows in the decreasing or non-increasing order of the weights. So, from this incidence matrix, we can now get this incidence matrix. Now, we repeat the same thing to rearrange the columns by giving weights to the row positions. Therefore, the weights for the row positions will be 1, 2, 4, 8, 16, 32 and 64. These are the weights. Now, using these weights, once again they are of the order of 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, etc. So, the weight corresponding to this column will be 64 plus 32. Now, for better understanding, the weights are already shown here. So, 64 plus 32 will give us 96. Here it is 16 plus 8, 24 plus 4, 28. Here it is 16 plus 8, 24, 2 plus 1, 3, 64 plus 32, 96, 4 plus 2 plus 1, 7, 64 plus 32, 96, 64 plus 16, 80, 88 plus 4, 92. So, the weights corresponding to the 8 columns are now calculated by assigning weights to row positions. The assigned weights or fixed weights to row positions are shown here. Using these, we compute the column weights for each of the column as 96, 28, 24, 3, 96, 7, 96 and 92. Now, the columns are sorted or rearranged in the decreasing or non-increasing order of the weights. So, we could start with 1. So, 96, 96, 96, then 92, then 28, 24, 7 and 3. So, the order will be 1, 5, 7, 8, 2, 3, 6, 4. So, 1, 5, 7, 8, 2, 3, 6, 4 is the order. Now, it is rearranged according to this order 1, 5, 7, 8, 2, 3, 6 and 4. So, now you see that the order is 1, 5, 7, 8, 2, 3, 6 and 4. Now, this is the rearranged order after rank order clustering. Now, when we look at this, we observe that we will get a structure like this. Now, from this structure, now you see that the rows are in the order 3, 5, 4, 6, 1, 2, 7. Columns are in the order 1, 5, 7, 8, 2, 3, 6 and 4. Now, when we look at this structure, this is a block diagonal structure, where all the ones in the form of diagonal blocks are kept closer to the diagonal. The zeros are off diagonal and they are far away from the diagonal. So, this is block diagonalizing the given 0, 1 matrix. Now, when we from this we can identify 3 groups, where 3 and 5 will form one group, machine group with parts 1, 5 and 7. Machines 4, 6 and 1 will form another cell which will make parts 8, 2 and 3, and machines 2 and 7 will form the third cell which will make parts 6 and 4. There are 2 intercell moves that are shown here in red color, and these intercell moves involve component 8, which is attached to group number 2, will visit machine number 3, which is in group number 1. Similarly, component number 6, which is attached to group number 3, will visit machine number 1, which is attached to group number 2. So, there are 2 intercell moves in this solution. So, rank order clustering is a very simple way to try and get a block diagonal structure out of a given 0, 1 incidence matrix. Therefore, rank order clustering can be used to create machine cells and part families exactly the same way as we have described. Now, this algorithm called rank order clustering comes from contribution of King in the year 1980 and subsequently made better through another paper by King and Nakan Choi, which came in 1982. Now, let us try and apply the rank order clustering to another matrix. Which is given here. In fact, before we go to this example, let us revisit the previous one, where we started with this incidence matrix. We started with this incidence matrix, and then we finally got a solution, which is this. Now, when the initial rank order clustering algorithm was first proposed, we were giving weights like this, had indicated that the weights corresponding to these 8 columns would be 1, 2, 4, 8, 16, 32, 64 and 128. Similarly, the weights corresponding to the rows were 1, 2, 4, 8, 16, 32 and 64. So, if one were to write a small computer program for rank order clustering, one has to do the multiplication with the weights and then identify a score for each row or each column. In this case the scores for the columns are computed based on the weights here. But then we observe that these weights are exponentially increasing because the weights are 1, 2, 4, 8 etc. So the 7th place here has a weight of 2 to the power 6 because this is 2 to the power 0, 2 to the power 1, 2 etc. So the nth place, or if there are m machines here, if there are m machines, then the topmost machine will have a weight of 2 to the power m, 2 to the power m minus 1. Similarly, when we were computing these scores, the weights were 2 power 0, 2 power 1, 2 power 2, 2 power 3 and so on. So if there are n columns, then the first column weight will be 2 to the power n minus 1. When we apply this technique to a real life problem, we may encounter matrices of the size say 50 by 100 or 50 by 200, which means we have to store somewhere a weight or a number of 2 power 199 if we had 200 columns. So this was seen as some kind of a limitation of the rank order clustering algorithm when it was first proposed, because at that time it was not possible to store a number as large as 2 to the power 199 and so on as an integer. Subsequently that was overcome by saying that we need not compute a score for each of these rows. If we go back to the algorithm, we gave a weight to each position which is 0, which is 1, 2, 4, 8, 16, 32, 64 and 128, and based on these weights we computed a score, and then we sorted them on the decreasing or non increasing order of the scores. It was quickly found out that it is not necessary to give a weight to each position and then compute a score. It is okay, or it is all right to treat this entire thing as a string of zeros and ones, which means this row will be a string of 0, 1, 0, 0, 0, 1, 0, 1, and by simply comparing the ones and zeros in the various positions, it is possible to sort them in the order that we want. For example, this string that has a 1 in the first place will come ahead of this, 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 this and this. So the only thing is to check whether 3 comes first or 5 comes first. Look at the next position, both are zeros. Next position, both are zeros. Once again both are zeros. Both are 1. Once again both are zeros. Both are 1. There is a 1 and 0, therefore 3 will come ahead of 5. So by simply sorting them and treating each row as a binary string, we can do a simple sort algorithm and we need not compute a weight associated with each row based on column position weights and then sort them, or alternately it is not necessary to compute a weight for each column as we did here using row position weights and so on. So very quickly rank order clustering algorithm was being implemented in the form that was described just now, that is by considering each row and each column as a string of zeros and ones and not by associating a weight which was exponential in nature. So that limitation of rank order clustering was quickly overcome and people could use rank order clustering for a very large sized matrix also. Now after this, let us come to another example of using rank order clustering or trying to understand are there other issues with rank order clustering. Now let us consider this as an incidence matrix with 6 rows and 8 columns. So 6 machines and 8 parts. Once again a small sized matrix, more for the purpose of illustration rather than duplicating a real life scenario. Real life matrices are much larger than the size that we are right now seeing. Now let us assume that this is the initial matrix and closer look will tell us that this is already sorted in the after the first sort. So, we do let us say 2 phases of rank order clustering, and after 2 iterations of rank order clustering, one for each row and one for each column, we would get a final block diagonal form like this. So, the final block diagonal form will give us 6 5 2 1 3 4 and 2 7 8 3 1 4 5 6. So, this will be the final block diagonal structure. Now, we get into the issue of how many groups do we want to create out of this, which machines go to which group and which parts go to which group. In the earlier example, when we had this, again the same question remained. This is the block diagonal structure that we got after 2 iterations of rank order clustering, one for each row and one for the rows and one for the columns. Now, we said that on closer look at this matrix, we find that there are 3 groups. Now, here we have to do this little carefully. Now, the best block diagonal structure that we can think of is a structure like this. There are 2 groups with machines 6, 5 and 2 forming the first machine cell, and machines 1, 3 and 4 forming the second machine cell. Parts 2, 7, 8, 3 visit the first machine cell, parts 1, 4, 5, 6 are attached to the second machine cell with 4 intercell moves. So, the point that I am making here is that rank order clustering per se or explicitly does not give the machine groups and part families. Rank order clustering gives only a rank ordered representation of the given matrix. So, essentially there are 2 stages to the algorithm. The first stage is to get the rank ordered matrix, which will look like this. The second stage is to create machine cells and part families using a matrix like this. Many times this is evident and can be seen through the naked eye, and we could make machine groups and part families. Sometimes different people looking at the block diagonal structure may create different solutions, which means different configurations of machine cells and part families, or we need another algorithm which will identify machine cells and part families from a given block diagonal structure that comes out at the end of the algorithm. So, when we have something like this as the final structure, when we have a structure like this, now we realize that this is the final solution. Now, a typical PFA solution, we have seen this slide earlier in our example for the 16 machine 43 part example. A typical PFA solution will be like this. It will give the machines belonging to each group and components belonging to each group. So, the end of the production flow analysis algorithm, we would get exactly how many groups we have, what are the machines that go to each group, and what are the parts that go to each group. Now, from this table we could create this matrix, whereas in a rank order clustering we actually have this matrix, and then from this matrix we draw these 2 lines. It may look simple that we are just drawing 2 lines or we are partitioning it, but after the partitioning we can get the tabular representation where we would say 6 5 2 belongs to the first group, 1 3 4 belongs to the second group. Now, this by itself can become subjective at some point, and we need additional effort to do that, and we may get different solutions depending on who is doing it. Now, what are the issues in rank order clustering? The first one is to identify groups from the final structure, which is what I described right now, whereas PFA we get the groups and then we create the matrix. In rank order clustering, the matrix is given first from which we have to create the groups. Then the effect of inter-cell moves, this aspect is very similar to that in production flow analysis. Whether we use production flow analysis or rank order clustering, we finally get machine groups and part families, we get inter-cell moves. These inter-cell moves will have to be eliminated, and we have to fall back on the 4 ways that we saw in the earlier lecture to eliminate or minimize inter-cell moves. These 4 are: can I carry out with an existing machine, can I alter the production plan, process plans in such a manner that it is possible to do it here, or can I make some small engineering changes and execute it, should I duplicate a machine or buy a slightly less expensive machine and put it there, or do I carry out part subcontracting or operation subcontracting. So, these are the ways by which one can minimize inter-cell moves. Next one is to understand, are there problems or situations where rank order clustering may not do well. For example, if we consider a matrix like this, this is another example of a machine component incidence matrix. This example has 10 rows and 20 columns, which means 10 machines and 20 parts and components. Now, if we carry out rank order clustering by doing it first for the rows and then for the columns, we will get a structure like this. Now, this matrix has been specifically created so that we get a very nice structure here. So, the second part of the algorithm, which is actually identifying machine groups and part families from a given block diagonal structure, is very simple in this particular structure, because it is very evident that there are 3 groups. Now, you see all the ones are clustered beautifully together. There are 3 distinct blocks, all the zeros are outside of the blocks. So, the second part of identifying part families and machine cells is easy. So, this type of a matrix is called a perfectly block diagonalizable matrix or well structured matrix. Sometimes we have what are called badly structured matrix, which are occasionally called as ill structured matrix, and in such instances rank order clustering becomes a little difficult, in the sense the algorithm will give you a solution like this, but then the task of identifying part families and machine cells becomes difficult when we use a method like rank order clustering. Now, there are ways to overcome that. Now, we can, for example, we have this, and let us say we do this classification, and for some reason we understand that this classification has 4 inter-cell moves. Sometimes by closely looking at a matrix, we would know that there can be some rows or some columns which actually have an unusually large number of 1s. So, we know that such columns or such rows or such machines or such parts will create inter-cell moves. So, sometimes we can remove a particular part, or we can even remove a particular one from the matrix and then carry out rank order clustering, and the whole order of the final block diagonal form will become very different. Now, those things come out of experience. After that, we can put back the one in the corresponding position after we have block diagonalized. In fact, when we go back to production flow analysis, Burbidge also gives certain interesting thumb rules when we do the group analysis. If you remember, this is a solution that comes from our 16 machine 43 part matrix. Now, if we see this very carefully, we know that 6 and 8 are 2 machines which have a very large number of components visiting. In fact, Burbidge says that if there is a machine where all the components visit, now actually take it out of the analysis, and after the analysis duplicate it in every cell. If there is a machine where only one part visits, once again take it out of the matrix, and after production flow analysis put that machine back into the cell where that part visits. Similarly, if there is a part which visits all the machines, take it out of the analysis and then see what more can be done, because such a part will create intercell moves, which will also in a way, if you have a part that visits all the machines, if you see the way the production flow analysis works, because we create complete cells for each part, the cell where such a part is assigned will have all the machines, and because it has all the machines, every other module will be a subset of that. So, all of them will be merged to give you a single cell with all machines and all parts, which you do not want. So, take out such parts from the matrix and then proceed. So, one of the best ways of overcoming this limitation, where you are unable to get the nice block diagonal structure, is to do the rank order clustering once, find out which are the positions that will definitely be intercell moves, take those ones outside, then apply rank order clustering again, so that in the end you get a very nice structure, and then you can put back all those ones that have been taken away from the matrix in the right positions, and then see where the intercell moves exist. The last one, of course, is in many practical situations we want to restrict the number of cells as well as to restrict the cell size. Once again, if you go back to one of the slides that we have seen in an earlier lecture, where I had spoken about applications, I had said that the large cell size examples did exist. There were cells that went up to 15 machines and so on. So, many times as the cell size increases, we understand that the control on the cell comes down. So, smaller the size of the cell, the better it is. Many times a reasonably large number of small sized cells is desirable, rather than having a very small number of very large sized cells. So, we need to look at these two aspects of cell size and number of cells. Both production flow analysis and rank order clustering explicitly does not address this, but leaves it to the decision maker to incorporate these aspects. Because when we look at the PFA solution, or when we look at a rank order clustering solution, there could be times when you have one slightly large cell. We have seen that in an earlier example, where a particular cell had 11 machines. Now, do we want to create a cell with 11 machines, or do we want to create a cell with 8 machines? We saw in the previous example that the one that had a cell size of 11 involved 7 extra machines, whereas the other alternate solution that had 8 machines in a cell involved 8 extra machines. So, cell size and the number of cells is also a factor which is not explicitly addressed in the algorithm, but the decision maker is given the flexibility and the freedom to choose these two parameters and adjust the cell configuration after the solution from these two algorithms are obtained. Well, now having seen rank order clustering, let us move to some similarity based methods. Now, before we understand what similarity based methods are, let us once again revisit this simple example. We have seen this example. This example is the one that gives us a perfectly block diagonal structure. Now, when we did rank order clustering for this, very quickly we observe that if we take weights and then do it, or if we treat each one as a string, now 1, 4 and 7 are together, you see 1, 4 and 7 they are identical, that is why they are together here. 2, 6 and 9 are identical. So, if you keep 1 and 4 next to each other, you realize that those two strings are perfectly identical. 1 and 7 are identical, 4 and 7 are identical, and so on. Now, we can say that 1 and 4 are also similar, they are the same, they are similar. how did it happen? If we now translate this information that we have here, the block diagonal structure, into a real life scenario, we now say that there are machines 1, 4 and 7 which process parts 1, 4, 9, 15, 16 and 20. Now these 3 machines 1, 4 and 7 will not be similar machines in terms of its configuration. For example, if you say that there is a part number 1 that visits 1, 4 and 7, it is quite likely that 1, 4 and 7 are different machines. One could be a lathe, one could be some grinding and so on. But they are similar in the sense that all of them are processing parts 1, 4, 9, 15, 16 and 20, because of which the rows were the same. So we could go back to rank order clustering and say that if 2 rows are identical, then those 2 will come one after another, which is also true, because if 2 rows are identical, they will get the same score and therefore will come one after another. Example we have seen here in the earlier ones, we have seen here that these 3 columns are identical because they have the same weight, same 1, 2, 1, 2, 1, 2, identical columns, they have the same weight and they come together as 1, 5 and 7. Whereas these 2, they look very similar, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0. They look very similar, but they are not identical. So they can come next to each other, they may come next to each other 2, 3 and so on. So what we can do now is to try and find out some kind of a similarity index or a similarity coefficient between the rows and then start grouping them based on the similarity coefficient. So those methods are called similarity coefficient based methods. There are several ways of defining the similarity coefficient. So we are going to see one way of defining a similarity coefficient. Now let us look at this matrix. Let us look at this matrix and let us try and compute some similarity coefficients. Now this is our incidence matrix, once again a very small sized incidence matrix. Now there are 6 rows representing 6 machines. So we construct a similarity coefficient matrix among the machines or among the rows. So this is a similarity coefficient matrix among the machines or amongst the rows. Now what is the similarity between 1 and 2? Now the similarity between 1 and 2 is computed to be 1 by 7, which is based on this formula, which we have to explain now. So if we take rows 1 and 2, one has component numbers 1, 4, 5 and 6 visiting. This has component numbers 2, 6, 7 and 8 that are visiting. So the first thing we do is, which are the common components or how many common components are visiting both 1 and 2. Now if we see these 2 rows carefully, there is only one common component visiting, which is component number 6, which also means there is only 1 1 pair. All other pairs are either 1 0 pairs or 0 1 pairs or 0 0 pairs. If we take these 2 rows, for this component it is a 1 0 pair, for this it is a 0 1 pair, for this it is a 0 0 pair and for this it is a 1 1 pair. 1 1 pair tells you that this component is visiting both the machines. So, the number of components visiting both the machines is 1, which is the numerator, and if we bring these two machines together, how many components will visit either of them, which means we should look at 1 0 pair, 0 1 pair and 1 1 pair. We leave out only the 0 0 pair. If we do that, we realize that this is a 1 0 pair. So, component 1 will come, component 2 will come, 3 will not come, 4 will come, 5 will come, 6 will come, 7 will come and 8 will come. So, the union set is 7. The union set is the sum of the 0 1 pairs, 1 0 pairs and 1 1 pairs. So, the union or the number of components that will visit either of the machines or both the machines is the denominator. So, the numerator is 1, the denominator is 7 and the ratio is 1 by 7 for 1 and 2. Now, let us look at 1 and 4. If we look at 1 and 4, we have 1 0 0 1 1 1 0 0 and for 4 it is 1 0 0 0 1 1 0 0. So, which are the common ones? The numerator will have 1, 5 and 6. So, there are 3 parts or components that are visiting both 1 and 4. So, the numerator is 3. The denominator is 1 has 1, 2, 3 and 4. This has 1, 2 and 3. So, denominator will have 1 visits both, 2 is not counted, 3 not counted, 4, 5 and 6 come, 7 and 8 are not counted. So, only 4 components 1, 2, 1, 4, 5 and 6 will visit both 1 and 4 or either 1 or 4 or both if they are combined together. So, denominator is 4, numerator is 3 and therefore, the similarity coefficient is 3 by 4. Like this, we can construct the similarity coefficient matrix. This matrix is actually a symmetric matrix, but only 1/2 of the matrix is shown. The diagonals are not explicitly computed because similarity between a machine and itself is always 1, and we do not require the numbers in the diagonal because our idea is to bring the machines together and group them. So, a number here in the diagonal is not going to add value to the purpose for which we are computing this similarity coefficient. So, a similarity coefficient matrix is always shown as a shown either as a upper triangular or lower triangular with only the diagonal not shown and only one part of the triangle is shown. So, here we show this matrix as an upper triangular matrix, which is a 6 by 6 matrix because we have 6 rows here. So, we compute this similarity coefficient. Now, look at this 0, 3 and 5. 3 has 1, 4 and 6, 5 has 2, 3, 5, 7 and 8. There is no part that visits 3 and 5. So, numerator is 0, denominator is 8, therefore, it gets 0. So, similarity coefficient is always between 0 and 1, it is not negative. Now, using this similarity coefficient matrix, we now try and group the machines. And how do we do that? Now, we look at the first one and we realize that the maximum similarity is 3 by 4. 3 by 4 is 0.75. The next one is 4 by 7, which is less than that. So, the maximum similarity is 3 by 4. So, we can either group 1 and 3 first or 1 and 4 first. So, we could group that and we start the first grouping by saying that machines 1 and 3 are grouped first, then the rest of them are grouped. So, the next matrix that we will have is a 5 by 5 matrix where 1 and 3 are grouped first, 2, 4, 5 and 6 remain. Similarly, 1 and 3 are grouped, 2, 4, 5 and 6 remain. Now, we know that given 1 and 3, we can compute the similarity coefficient using the formula that we used. We could compute the numerator and the denominator, and we could do that. But once we form 1 and 3 together, how do I calculate the similarity between this 1 and 3 and 2? So, to do that, we go back to this matrix, the earlier matrix. So, similarity between 2 and 1 and 3 is 2 to 1, the similarity is 1 by 7, 2 to 3, the similarity is 3 by 4. So, we go back here. So, 1 and 2 by 3 is seen as 1 by 6. Which is the smaller of the similarity. 2 to 1 similarity is 1 by 7, 2 to 3 similarity is 1 by 6. So, the bigger of the two, 1 by 7 and 1 by 6, the bigger of the two is taken as the similarity between 2 and 1 and 3. Similarly, between 4 and 1 and 3, 1 to 4 is 3 by 4, 3 to 4 is half. So, 3 by 4 is taken, 1, 3, 4 is 3 by 4. Similarly, 1 to 5 is 1 by 8, 3 to 5 is 0. So, between 5 and the group 1, 3, the maximum of them, which is 1 by 8, is taken. Similarly, 1 to 6 is 1 by 4, 3 to 6 is 2 by 7, and 1 by 4, which is bigger than 2 by 7, is taken. Now, the rest of them are easy. 2 to 4 is 1 by 6, that comes from the same matrix. So, we now have a 5 by 5 matrix, and then we look at which is the maximum similarity. Now, you realize that 3 by 4 is the maximum similarity. So, 4 goes to 1, 3, and the next set will be 1, 3, 4 together as one group, 2 as another group, 5 as another group, 6 as another group. So, we now generate a 4 by 4 matrix from this, where the first row will be 1, 3, 4, 2, 5 and 6, column is again 1, 3, 4, 2, 5 and 6. Now, we follow the same approach. From this matrix we can create the next matrix by taking the maximum of the similarities, and if we continue with this process, finally we will get, at the next iteration we will get 4 groups with 1, 3, 4, 2, 5 and 6. Then we will get 1, 3, 4, 2 separately, 5 and 6 will go together. Then we will have 1, 3, 4 together, 2, 5, 6 together, and then we will have all of them coming together. So, we would started with a solution where each of these 6 machines or 6 rows were 6 different groups. From there we came to a solution with 5 groups, where 1 and 3 was grouped together. Then we came to a solution with 4 groups, where 1, 3, 4 was grouped together. Then we come to a solution with 3 groups, where 1, 2 and 3. Then we come to a solution with 2 groups, and then we come to a solution with a single group. So, if we say that we want a solution with 2 groups, we would now take this solution with 1, 3, 4 and 2, 5, 6 as 2 groups. So, we would go to the solution with 1, 3, 4, 2, 5, 6 with 2 groups, which is the solution that we have here. So, if we want a solution with 2 groups, we will have this 134 and 256 as 2 groups with 4 intercell moves. So, this is one of the similarity coefficient based methods. Now, the method that we have seen is called a single linkage clustering algorithm. It is called a single linkage clustering algorithm. It is a clustering algorithm because it uses clustering methods to form groups. It is called single linkage because when we at this stage, when we computed the similarity between 1, 3 and 2, we took the maximum out of 1, 2 and 3, 2. For example, we took the maximum out of 1, 2 and 3, 2. When we take the maximum, it is called single linkage cluster analysis. Now, once we identify 2 groups and a solution from here, which is 1, 3, 4 and 2, 5, 6, we have to now get the part families. Now, one of the ways of getting the part families is to do the same similarity coefficient now for the parts instead of the machines. Here we have done similarity coefficient for the machines, we can do similarity coefficients for the parts. So, that will be an 8 by 8 matrix, and from 8 we go to 7, 6, 5, 4, 3, 2 and 1, and then find out the solution where there are 2 part groups, and we will realize that the 2 part group solution will be this with 1, 4, 5, 6 and 2, 3, 7, 8. So, then we can create the final block diagonal structure and get machine groups and part families. Now, machine groups and part families can be formed separately for machine groups as well as separately for part families. Another way of doing it is, once we form machine groups, we say we have 2 machine groups with 2, 5, 6 and 1, 3, 4. Now, part families can be easily formed by looking at this. Look at part number 1. Part number 1 requires 6, 1, 3, 4. So, which of these groups will it go? It will go to 1, 3, 4 because there are more machines. So, part 1 will go to the group with 1, 3, 4. Part 2 requires 2, 5 and 6. So, which group will it go? It will automatically go to the machine group with 2, 5 and 6. So, if we follow this simple rule of allocating parts based on an existing machine configuration, most of the times we get similar results, and we could get the part families automatically from this. So, other issues related to single linkage cluster analysis we will see in the next lecture, where I will also try and explain what exactly is this single linkage, and at the same time I will also introduce you to some basic principles of cluster analysis and how this algorithm comes out of cluster analysis. We will see all those aspects in the next lecture.